Hi, my name is Shajid, and we have a poster set up on RVS, basically the RISC-V verification suite for architectural compliance and functional testing. So basically we have a tool called a Sting. So what it basically does is it lets you write to tests, extend tests, and along with the tool itself, we actually have a package. So we have this tool called Sting. So basically, along with Sting, we have a large number of tests, and the idea behind the tests is that you can have verification of the any RISC-V implementation. So these tests are basically based on the scenarios that we have identified. So what we have done is we've come up with a test package, and based on this test package, we have developed the test plan. So the difference between a typical, say, a RISC-V test and what we actually do is that, so when you rerun these tests, right, so it generates an n number of configuration. Instead of having one single configuration, you can have a lot of these configuration. These tests are all portable, so you can run it on simulation, emulation, and you can also run it on the FPGA and silicon. Okay? And then we have, so in Sting actually has got a test kernel. So the kernel itself is used as a test harness on which you run the actual tests, and basically the harness will then do stuff like it will manage the memory for you, lets you know the status of the test. So verification packages can be created easily for, like, if you have an extension in the RISC-V implementation, what you can actually do is you can extend the verification package, and then Sting will let you generate this test on the extensions. So all the tests that we generate are actually architecturally correct. So these are like, there'll be no, so it's guaranteed that the tests are like made sure that it generates the correct tests. There are no false failures. Any false failure that comes is actually on the tool itself. So we actually run this on Rocket and Pulpino. So in the Barcelona presentation and in the Barcelona conference, we actually gave a small talk on how we used it on the Pulpino platform. We actually found about 30 bugs overall on the Pulpino platform. About 5 of them were quite critical. So we found a bug in the multiply unit, which was like a fairly critical bug, and which caused the designers to change the design. We also, so the Google actually used the RISC-V core for their internal visual core. So what they did is they wanted to use the hardware accelerator in the RISC-V core. But because we found many bugs with interrupts and the hardware loop system, Google decided not to use that feature. So we support RV32 and RV64. IMA, the F and D parts are still in work, but we support the compress and the rest of the instructions, and the atomics also. It supports multiprocessor, so you can write tests, hand code tests, and tell that I want certain sequence of code to be executed on, say, CPU 0 and certain bit of code in CPU 1. So it could be like, we have actually tested this. So this is actually, this tool actually works for the ARM architecture also. On ARM architecture, we have actually booted this on 16-core CPUs, but in RISC-V, we have actually tested this on 4 cores. Okay, and so we have things like coverage and other regression-related tools that we package along with the tool itself. So today morning there was a talk on Rita. So we have actually developed something similar to that, but but we also have things like whether an interrupt occurred, when a given instruction happened, and we've actually used to find out like the delays that happen for each instruction. So we actually found out a kind of performance bug in the RISC-V core, wherein during one of the division operation, it took a lot more cycles than it was expected, and then they found out that they needed to change some things in the implementation of the div to make it go faster. So one thing that any tool worth its salt needs to do is that it needs to give a lot of debug information, because usually most of the time that's spent is like in debugging, figuring out what the test was actually doing. So Sting actually gives like a lot of details when a failure happens. When the test is generated itself, we print out a lot of metadata, and we also have small scripts to help you backtrack to the point of failure and then come up with the failure itself. So there are more things that I can talk about. We'll, if you just come around during the poster session, and then we'll discuss this more. Okay, thank you.
Thanks very much. My name's Kevin McDonald. I'm from a company, Impirus, based out in the UK. And I think, as somebody said earlier, we're a team of dedicated, hard-working engineers that produce very good tools and technology, and there's a small overhead that gets to go around and visit conferences and speak a little bit about our activities. I'll be giving a poster session. If you're available, please stop by. And I can talk about the way we can use software simulation to kickstart your projects. We've heard a lot today about the ISA. The ISA is one of the most important technologies and standards in our industry. It's the barrier between hardware and software. What we do is we help you kickstart software early before you've got an SoC. Before you start development, you can start on your software projects and get things working. A key technology is our simulation, but we provide software models of processors and SoCs in software, in open source. So this allows you to accommodate changes as your development. All right. So within the RISC-V family, we've produced models across the whole spectrum of the current specifications. We've also worked with Andes and Sci-Fi's to build implementations of their platforms. I think there was a comment earlier about somebody not having boards available due to a supply issue. This is exactly why you need virtual platforms to help your customers work while they overcome those delivery. We provide platforms as open source, which allows you then to modify those as you change and develop your chip. We provide software tools that help you do debug across your entire SoC. Modern platforms are going to have multiple cores in clusters. These will be different architectures. You need one tool that's going to look across the entire SoC and help you debug those critical interactions. And then within the RISC-V Foundation, we're very active in the compliance group. This is very important to make sure that the processor you receive or the processor you design is completely characterized to the specification as you intend. This also allows you to build custom extensions as you evolve your platform and make sure you have not affected your core compatibilities. We're working with customers on RTL, and we're happy to check and verify and offer this as a compliance suite. Thank you.
Hi, this is just a preview of the poster I'll be talking about, so any detailed questions we can talk over there. So this is just how multi-level interrupts are being designed in the Linux kernel that supports RISC-V. So that's what this poster is all about. So first, as this is a hardware consortium and everybody in one way or other way is related to SoCs, processor designs, it's needless to say that low interrupt latency is one of the key for high performance systems. So when we design or anybody designs systems with the interrupts, there are different design choices. We can have global only interrupts, but with the pros that you can do easily multiplexing, and then one signal gets delivered to the CPU, but that incurs high interrupt latency because you have to always arbitrate every interrupt, and then that gets delivered to the CPU. On the other side, other spectrum of it, you can have local only, where you can do with the minimum latency because all interrupts are directly connected to the CPU, but you have a huge hardware complexity which is not feasible. So the best design choice is always multi-level. You cascade, so where the interrupts that can have some kind of interrupt latency, that can manage some kind of interrupt latency, you hide them behind interrupt controller, which multiplexes all of them and send one signal, and then the high priority interrupts basically directly gets access to the CPU, and those are with the minimum latency. So that's the obvious design choice RISC-V adopted. And so we have two different kinds of interrupts in the RISC-V. One is the platform level interrupt controller, which manages all the external interrupts. So, and this interrupt controller does all the prioritization and routing of the interrupts and heart arbitration or CPU arbitration. Basically, let's say 10 interrupts are connected. It decides when interrupt gets signaled, which CPU gets the interrupt. And all these external devices are connected to PLI, PLIC, and then PLIC is basically connected to the hub CPU. And we have local interrupts, which has a timer interrupt, software interrupt, and the local interrupts are basically local external interrupt, which are CPU interrupts. And since since I'm talking only in terms of Linux support, how it's designed in the Linux, like how we implement it, I'm going to talk about how the U54 core from Sci-Fi, which is the only core that has Linux support, manages it and is actually implemented it, and then how we manage it in Linux. So this is just a brief overview of how it is implemented, how Linux views as the hardware. As I said, all of the devices are connected to the PLIC, and then there is a HLIC, which is known as heart level interrupt controller. This is just a modeling of all the CSR register in Linux, and which manages all the PLIC from this side and all the local timer and software interrupt from that side. And this is how the interrupt management design in Linux. So this is whole lot of information. So I probably would like also to come to me if you have any detail, you want to know the more details, how exactly it's designed in the Linux, how we try to have minimal interrupt driver code and reuse as much as core Linux interrupt management code is there. So that's this diagram speaks about. So I'll probably happy to talk with you with all the details. And see you at the poster session. If you have any questions, we'll talk there. Thank you.
Okay, so my name is Thiago. I'm a PhD student at the CEA in France. And I'm going to talk to you about one work that we've been developing. It's actually more academic so it's academic research and less industrial. So it's going to be a little bit different from what the other people presented here. So actually the main motivation for our work is the fact that some growing number of applications in the scientific computing community, they require a little bit more of precision than we are supposed to have, for example, in the IEEE standard. So this means that we have some challenges in terms of increased application numerical stability, ensure also the convergence of iterative algorithms, and we have to compensate also for the yield conditioning issues. So the solution that we propose for this is to use adaptive or variable precision format to address these problems that I mentioned. So for that, we propose to augment RISC-V with variable precision support. So the idea is that we have a coprocessor that supports this variable precision format, an ISA extension for the RISC-V, and also a programming model. So just to give you an overview here, so basically we augment a RISC-V processor with a coprocessor that can implement these variable precision operations. So that way we also have to handle unaligned memory access. We have to keep the memory footprint compact, and we also have to do the conversion between the data memory and the register file that is going to operate inside the coprocessor. And one thing that is very important in this architecture is actually how the numbers are stored in memory. So we use a UNO format, which is basically different format from the IEEE, which give us some metadata information inside this number in order for us to tell how many bits we have for the exponent and for the fraction. So that way we have different numbers with different precisions with the same format. And inside this VP coprocessor, we have also a scratchpad, which will actually be mapped as a register file, so with different chunks. So that way we can have some numbers having more chunks or less chunks, representing that way the variable precision format that we want in these operations. And also, along with that, we have an ISA extension for the RISC-V. So this actually is just a work in progress. It's a joint work between the hardware group and the software group at my company. And as future works, we plan to measure performance and energy consumption and do the work in the compiler, and of course validate all this and experiment with real-life applications. So if you have any questions about this, come talk to me in the poster section. Thank you.
Okay, this is a RISC-V conference, and so what I'm going to say now is probably considered heresy. So ISAs are good enough. Sorry, there are ISAs, the RISC-V has an open ISA, but actually that's not good enough on its own. You need to implement the ISA, and you implement it in RTL and you call it a core. Actually, that's not enough either. The core sits in an SoC, and the SoC has a bunch of IP blocks, either custom IP blocks or bought in. So that makes an SoC. For a product, that's not good enough either. For a product, you need to have a bunch of software to run on top of that. And that software needs to work in conjunction, in harmony with the underlying hardware. And in order for that to work, what you need is understanding of the system to behave properly. And so the purpose of my demo, it's not a poster, it's a demo. What we'll have is a heterogeneous environment, because that's what proper products will have in the near future, and for the foreseeable future. In this demo, we'll have a dual-core ARM system with a RISC-V core with debug logic and a trace encoder. And then there'll be a bunch of IP blocks that we provide. As I mentioned earlier, we have 3 classes of IP that will help provide with visibility and show processor trace deadlock in one environment. So the demo will show bus transactions, i.e. bus bandwidths going from to and from various cores to the DDR controller, traffic, processor run control. It'll also show a deadlock situation. Of course, you never get deadlocks in real SoCs, but we have an FPGA, so we can cause that. And all that will be driven from one console. It'll be the IDE, Eclipse-based IDE, which will show both run control, SoC visibility, and processor trace. So come and see the demo. Thanks.